Here we have a series of numbers, and we're going to try and solve it in a way that will give you some insight into the rules of sigma notation and to exploiting the Gaussian sum that we just saw. Now maybe you see the answer already, but notice that if we factor out a 2 here, oops, we can get something kind of nice where notice that the inside here, this is the Gaussian sum that we saw. And I could rewrite this as 2 multiplied by sigma n. Oops, I made this mistake. Of course, the endpoint is 2500, not 1000. The endpoint's right there. And the starting point is 1, right? And so I can rewrite this expression according to this one right here. And I could also have written it like this. These are equal to each other. Right? Let me just, could even make the equal sign bigger. They're equal to each other. So sigma notation is additive. So if I had an example like this, suppose I wanted to add, I'll make it a finite example. I've got n plus 1. And just to be clear, I'm going to put brackets around it so you understand that I'm summing. My summation includes that constant 1. The answer to this is going to be 1 plus 1 plus 2 plus 1, or I should say the expansion of this. That answer's not exactly the wrong word. Plus 1, and so we get 6 plus 3, which equals 9. But looking at it a little more carefully, I could write we've got 6 plus 1 times 3. And since we're starting at 1 and we're ending at 3, notice that this 3 is like the end point, and I could write 6 plus 1 times n if n was equal to 3. Now generally, if we have the sum of little n equals 1 to big N, n plus c, where c is equal to a constant number, right? It's a constant number. Then this thing is going to be equal to the sum of n and c. We're going to add up c n times, and that's the very definition of multiplication. I'm going to write this one more time just to show you, make sure that you get it. So we've got the sum of little n equals 1 to big N, and I can separate these two. So I'm summing up the n's and I'm summing up over the constant c, and then I end up with that kind of Gaussian sum in the first term, and the second term is just going to be, I'm adding C and capital N times, so I'm going to have C N over here. Oh, and I see that there was a little typo here. That should have been capital N. The concept of homogeneity comes up very often in economics. It comes up in macroeconomics. It comes up in a bunch of different contexts. And one thing to remember for you, especially if English is your second language, homo means same. So homogeneity is sameness. So these are sameness. And it's very easy to demonstrate if I've got something like the sum, and I'll just do it abstractly here. Okay. And maybe I've got, well, let's use pi, right? Pi, you all know what pi is, and pi is a constant number. And say it's multiplied by n, well, I could just factor out. I could just factor out or bring out the n, or not the n. I'm going to bring out the pi. I can bring out the pi. That sounds kind of tasty. I bring out the pi, and I'm left with pi multiplied by the sum here, this thing. And, you know, I could even write this out. I could even use the Gaussian summation, and I'd have pi multiplied by n plus 1, and the whole thing divided by 2. And of course, this is true not just for pi, but true for any constant number. Right? When we say constant, we mean a constant number. Here's a question for you. See if you can write it in a simplified equation. So I want you to essentially solve it. Solve it using a simplified equation. As a hint, you might want to use sigma notation to help you get to that answer. Maybe I'll write that down. Use sigma notation to help. And this is the point where I suggest you press pause on the video, take a moment, try it yourself, use the techniques that I just showed you, and then when you're ready, press play and we'll walk through the solution together. This time we have a rather plain series, but it's got a common factor of 1/2. So if we want to solve this, we can take out the 1/2, and then we're going to get 1 plus 2 plus 3 plus dot 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 plus 155. Oops. Oh no, that's right. Plus 156. Once we've done that, we've got the 1/2, and we could write this as a sum if we wanted. Maybe we're not going to need to use. I'll set the index to equal to I, and we've already shown that this thing is going to be equal to, well, in this case it's going to be 156 times 156 plus 1 divided by 2. And so I'm going to use a calculator, and my answer is 6,123. Here's an iClicker question. Press pause and try it yourself. And you can see that The correct answer is C. C is the correct answer. We want to sum from 125, starting from 125 and adding 1 and sum all the way up to 211. One way we could do that is to sum up everything from 1 to 211 and then subtract the parts that we don't want. So the correct answer is C.